get started. Welcome. I hear it's been a fairly uneventful week so far. So happily it's Friday. A couple of quick announcements for anyone who's visiting us. There's the Data Institute conference happening this week, so starting on Sunday, and then with workshops, and then Monday, Tuesday is the conference itself, so you can check that out. Registration's online. Those are our certificates that are happening in the spring a little later, March 18th and 20th, Deep Learning Part 2 and SQL, also space available online, registration for those. And we can jump right in and get started. So we're really happy to have Tyler Bettilyon with us today, and he's going to talk to us about machine learning on databases.
All right. Hi, everyone. Is this working? You can hear me? I don't think so. How about now? There we go. All right. Cheers. Okay, so slides are up. Thank you for having me. I'm happy to be here. Oh, still not working, huh? I got the green light. It's working now. Okay, I'll just keep looking down and make sure I don't turn myself back off, just in case. Okay, cool. So thank you very much for having me. I'm happy to be here. This talk is about machine learning in databases, specifically some really interesting research done about 2 years ago by Google and MIT, a collaboration, paper called The Case for Learned Indexes. So before we talk about learned indexes, I'll introduce myself. My name's Tyler Bettilyon. I used to work at some startups that you really don't care about, and I spend most of my time now teaching computer science and computer programming. I do some writing on Medium too about technology and its impact on society, so after you've heard me talk today, you can decide whether or not you care enough to look me up and learn a little more. So what's this talk about? It's about database indexing. And we're going to talk about some of the old stalwart algorithms that do database indexing. I hope it's not too much information review for some of you. But basically, indexing is a tactic for when you have a lot of data and you need to access that data quickly. So we've got a bunch of unsorted data, say, in your database table, 100 million records, and you need to find Tim in that data. You use one of these two strategies, either a hash table or a B tree. And these are super well-studied data structures. They've been around since the 70s. There's lots of interesting niche versions of each of these two overarching data structures that we can't get into, but I'd be happy to talk to you about them after, if you want to come up and chit-chat. But then, after I go over those two things quickly, we're going to talk about the learned indexing paper that I mentioned. You can find it on arXiv. It's a really cool paper. I highly recommend you read it. It's surprisingly readable for this type of research. Okay, and then finally at the end, after we've talked about all three of these strategies, the hash table, the B tree, and the learned indexing strategy, I'm going to spend some time comparing and talking about what the researchers learned, because it's not clear at all that the learned indexing strategy is going to always be better than some of these classical algorithms. There are some places where the classical algorithms still have a pretty significant advantage. So we're going to think about what the trade-offs are and why and when you might want a learned indexing strategy. Okay, so let's get right into it. What's indexing? Indexing helps us find data within an unsorted large collection of data. And this is especially helpful when we have to query that data quickly, right? I think that all makes sense. You've used SQL, you've been in database land before. So I've got, say, a big old database, hundreds of millions of rows, and each one of those rows is a single record. But I want to be able to answer the question, hey, where's Tim, right? If I don't have any indexing structure, the best thing that I can possibly do in this unstructured data is look through every single one of my 100 million rows and say, hey, did this one match the name Tim? What about this one? What about this one? What about this one? And you can imagine this strategy is, untenable as soon as you have any kind of realistically sized data, which as data scientists, I hope you're familiar with, having lots of data, right? So an index is a way to build a secondary data structure separate from the database itself that makes it easier for us to quickly answer the question, hey, where's Tim? So instead of asking each of these individual records, are you Tim, are you Tim, are you Tim, I can ask the index, the secondary data structure, hey, tell me where Tim is in my underlying database. The index says, hey, Tim's at offset 7, and I just go look up offset 7 immediately, without having to scan through any of the table at all. Okay? This is a super straightforward trade-off between memory and speed. We have to build the index. The index takes up memory. It makes it faster to do queries. So that's indexing in a nutshell. When we talk about indexing and how performant it is, we care really about 5 major considerations. And 3 of those considerations, the lookup speed, the insertion speed, and the deletion speed, are pretty much the same consideration. But we care about 2 types of queries, range queries versus point queries. And this is one of the big reasons that we have hash tables and B trees instead of just one indexing strategy, is that B trees are a lot better for these range queries when I want to find everyone who's aged 5 to 12 or everyone whose name starts with a T. I'll use a B tree for that. And when I just want to find one individual, hey, what's the individual with ID 7? Or what's the individual who's named Tim? I'll use a hash table for that. Okay, so we care about performance on different types of queries, point versus range. We care about how fast the actual lookup is itself. When I ask the index a question, its response time to me matters for us, obviously. And similarly, if I need to insert stuff into our database, I need to update the index to match, right? So if I want to insert Janet into my database, I have to make a record for her in my index as well, right? We care about how long this takes, and we also care about how much data that's going to require me to allocate, right? The size of the records in the index themselves. Okay, similarly, when I delete a record from the database, I need to remove that record from the index. If I don't remove it from the index and I ask the index a query, and it gives me an answer that no longer exists, that would be bad. So we care about how fast this is. And we care about the overall size of the index. If I'm indexing 100 million records, how much data is that index itself going to take up? And this is actually the place where the machine learning-based indexes have the biggest advantage over the classical algorithms. And this has a lot to do with machine learning being able to take into account the distribution of the data that's being indexed, whereas these classical algorithms like hash tables and B trees, a B tree is just a way to store the data in a sorted order, essentially. And a hash table is a totally agnostic algorithm to the structure and distribution of the data itself. We just compute some hash function that's basically random. That's maybe a little too flip, but. So there's a big caveat to this paper and a big caveat to some of these ideas in general. Most of the time when we talk about the efficiency of algorithms, we're talking about like big O notation, we care about the number of computations, the number of cycles, lines of code that are executed per lookup. When we talk about optimizing database index structures, we usually only care about how many times I have to access the hard drive. Because accessing the hard drive is orders of magnitude slower than, say, accessing some data structure that's just stored in RAM, or if you're lucky, accessing a data structure that fits, in a few cache lines on your CPU. So in these classical data structures, they've been extremely architected towards the idea of reducing database access, or not database accesses, but hard drive accesses, the number of times you go to the hard drive. And this paper only has concerned itself with in-memory data structures. So when we look at the results, we're comparing hash tables that fit in RAM to B trees that fit in RAM to machine learning, strategies that fit on your GPU's memory. So this is a pretty big caveat, and it's a place where the authors acknowledge we need to do a little more research, but just keep that in mind when we talk about the rest of these strategies. Okay, so I'm going to quickly review hash tables, or at least I hope it's mostly review for most of you. If not, hash tables are awesome. You should study them. Super cool idea. Love it. But hash table, basically, we take some arbitrary data in, the key that we're interested in. The running example I've been using is the name Tim for one of our records in our database, Tim's record. The hash function produces an integer. There's a bunch of different kinds of hash functions, like cryptographic hash functions, random hash functions, but these are typically fast. We do like 3 XOR operations. We get an integer out of whatever arbitrary data we put in, and we use that integer as the offset to our secondary data store, the hash table itself. Okay? Inside the secondary data store, the hash table itself, we store at that integer's location the memory in the underlying database, the actual memory address on our hard drive that record is at. Okay? So with our running example, Tim, I say, Tim goes into my hash function. The hash function produces 15. I go to my secondary data store, the hash table, at offset 15, and in that offset 15, it says Tim lives at offset, looks like I did 2. Tim's data lives at offset 2 to the underlying database. And I go there and look it up. Okay, and then I've got Tim's record. This is 2 hard drive accesses, if you're paying attention, right? The hash table lives in the hard drive in a classical indexing strategy. We might be lucky enough to have it fit in RAM, but typically you can't trust that. So 2 hard drive accesses. It's really, really good for individual point-to-point lookups. You know, I run the hash function on Tim, I get the address, access the hard drive once, access the hard drive a second time, boom. Pretty good, okay? Constant operation time, and this is constant both in terms of actual CPU cycles and in terms of hard drive access, which is not going to be true of the B tree. I'll try and point that out when we get there. Insertion and deletion are similarly constant time operations. If I'm inserting, I do the same thing, compute the hash function, get the integer offset for the hash table, and make the record in the hash table. Okay? Size and utilization, these vary. Most hash table strategies have to allocate about twice as much data as we have, you know, entries that we want to store in the hash table to avoid what's called a hash collision. So if I put 2 values into my hash function, Tim and Jane, let's say, and they both map to the number 15, now, you know, in this diagram I've got a problem because I have to put 2 things at item 15. There's lots of different ways to handle these types of collisions, but it's one of the big gotchas of hash tables, right? So we might use linear probing, we might use chaining, we might use cuckoo hashing. Cuckoo hashing is a great thing that lots of people have not heard of, and it's such a cool algorithm. Highly recommended. I've got some good reading, and one of the big pieces of pushback to this paper, actually, was a researcher at Stanford who said, hey, y'all, this was some really cool learned indexing stuff, but we've been doing better performance at higher utilization rates for, 10 years using cuckoo hashing and the power of 2 choices. Ooh! Yeah, pretty fun. Okay, so big caveats, and again, this is a place where the paper recognizes its limitations, is that insertions and deletions into a hash table might require you to rebuild the hash table. If we run out of space and we want to insert one more item into our hash table, we have to go allocate a new amount of space to accommodate our new item on the hard drive and copy everything from the old hard drive location to the new hard drive location. It changes the size of the underlying structure, so we need a new modulo. If we had 32 spaces, then we're computing the hash function mod 32. Now we've got 64 spaces, we're computing the hash function mod 64. So we can't just copy the memory directly. We have to recompute the hash function for every single entry, and it can be quite slow. So it's a huge source of concern for most hash tables, but in this paper, we were comparing only read only, create once, in memory, no insert hash tables. Okay, so this is another place where the learned indexes are a little weaker. Okay, so look forward to that. Okay, boom, B-trees. Next indexing strategy, the old stalwart. B-trees are really quite similar to binary search trees in some ways, in that they're basically just a way to store data in its sorted ordering without storing a list, making that sorted data easier to search. Okay, in a binary search tree, every node has at most 2 children, and you follow the left to get the smaller items and the right to get the bigger items. In a B tree, typically have on the order of hundreds of children per node instead of just 2. And they act a lot like, multi-volume encyclopedias, where you'll have the root node has 100 or so pointers, and the first pointer is like to all the records that start with the letter A, and the next one is to all the records that start with the letters B through D, and the next one is all the words that start with the letters E through G. And if we follow that down to its next internal node, then it has subdivisions there. So all the words between AA, like aardvark, and I'll have you know, AA is a playable Scrabble word. It's a kind of basaltic rock. So now you all learned something you didn't expect to. And if I follow all of those down to a leaf node, eventually in the leaf node, there's a store of the actual words themselves that are being stored, or the actual numbers themselves, whatever the data is you're indexing. Stores the actual data as well as a pointer to the underlying database record. where that word lives at. Okay? So B trees subdivide your data, and each time you travel down one layer in the B tree, you have finer grained subdivisions of that data. And when you finally get to a leaf node, you have the actual data itself. Okay? So when we use one of these things, like I was saying, these are highly optimized for hard drive access. When we build these things in most modern databases in practice, the size of each node isn't set. I said on the order of hundreds, and the size of each node is not set to like a limited size of entries. It's set by the amount of data that your computer grabs from the hard drive at once and stores in RAM. It's called the block size. So it varies computer to computer, but if you're in a highly optimized situation, you learn what your machine's block size is, commonly like between 4 and 10K, and you make that the size of your node. So the root node has 10K worth of entries in it, and if we fill them all up, good, then we have high utilization. But if we don't fill them all up, that's okay, because we're going to grab all of that data every time we access the hard drive anyway, so we might as well maximize the utility of grabbing all that data. And when we use one, we just grab it, we can scan through. It's super common to do a binary search since the entries are ordered, going back here. A comes, then B, then E, then H. So when we grab one block, we'll do a binary search on that block to find the particular subdivision that we should go to next. We'll go to that new node, grab the whole block, binary search it to find the leaf node, get the leaf node, binary search it to find the entry in the leaf node, and then finally, we'll get down to the actual piece of data we care about that maps to our hard drive address that contains the actual database record. Okay. So what's this good at? It's really good at range queries. If you think about those leaf nodes, and if you just think about all the leaf nodes, if you scanned the leaf nodes from left to right, you would be reading out the data in its sorted order. So if you want something that's just contained, I want all the items that start with the letter A, I follow that node down to the first leaf node that starts with A, and then just grab all the entries in that final leaf node. There's some common advances to B trees. You call this a B plus tree, where in addition to all the records, the final record in any leaf node is the pointer to the memory address of its next leaf node. So that I can continue scanning all the way from A to, say, Z, but just by going to the A leaf node first and then forgetting all the other internal nodes. Okay, so better at range queries than hash tables, but we pay a cost. It's log n now hard drive accesses in order to actually get the record we're interested in. Because the depth of the tree is, let's say it's got 100 branching factor, the depth of the tree is log base 100 of the total size of your data set. So I have to go down all the way through the hierarchy. That's log n cost in terms of hard drive accesses. And second caveat, in terms of just overall computational speed, forget the hard drive accesses, every time I grab one of those nodes, I also have to do a binary search on that node to find the particular subdivision that I should travel to next. So it's more computationally expensive, both in terms of hard drive accesses and in terms of actual CPU time. And again, size and utilization varies. It's not uncommon to have something like 50% utilization in a B tree. And the big factor on how full or utilized your B tree is depends on the size of your block. And so that's kind of out of our control because the hard drive manufacturer and the CPU control how much data we're grabbing from the hard drive at once. We don't have a lot of control. Okay, again, there's gotchas on inserts and deletions. Inserts and deletions might force the index to be rebuilt. And once again, the paper that we're talking about for learned indexes only dealt with in-memory, create once, read-only databases. So they don't have to deal with any of these expensive either rebalancing acts to make sure that we don't have like a tree that's really deep on the left and shallow on the right, and we don't have to split any nodes to make room. If we had one node that's fully filled and we want to insert something that belongs in that node, we have to split that node. But the learned indexes that we're comparing to, they don't have to deal with any of that. So speaking of learned indexes, now we're going to actually do some machine learning. Made you wait for a while, sorry. So here's the paper. You can find it on arXiv. It's a Google MIT idea. very interesting. And the core insight that started them down this path is, well, indexes are basically just doing regression. We're taking some arbitrary data and we're mapping it to a continuous space in memory. I mean, it's an integer space, but if we think about an index, especially a range index, as a cumulative distribution function, we're just, boom, estimating the position by saying, hey, take the key that you would have inserted into the hash table or the B tree, give that to your model, train your model on the order of your data, and then multiply whatever the model produces, the value between 0 and 1, by the number of elements you've got in your total data store. Boom, you've got the memory location. Okay, so this is the fundamental insight of applying machine learning to indexing. But there's a pretty big caveat. If you put something into a machine learning model and you're expecting the exact correct outcome perfectly with no error, all of you know you're going to be pretty sad. That's not going to happen. So because indexing is not like tolerant of even small errors, if we're doing like a weather app and I say it's going to be 77 degrees tomorrow and it's actually 75 degrees, your customer's like, yeah, dope, that was good, that worked. If I tell you Tim's memory address is 7 and his memory address is actually 6, and you grab, Tim's data, that's still 100% wrong. Being close is not good enough. Okay, but this is pretty easy to solve. The approach the researchers took was to say, while we're training, we're just going to keep track of the absolute smallest error, most negative error, that we ever produce while training. And we're going to keep track of the biggest error we ever experience while training. And then we'll just search in between those bounds for the data that we're looking for. Okay, not so bad. We're doing searches on B trees anyway, right? When we grab one of those nodes, we're still doing a binary search within that space. So maybe it's not so bad to have to search our index space at the end, all right? One super important idea here is, and this is another limitation of this idea, is we can only do this because there's no such thing as left out data. I'm not making predictions about data that I haven't seen in the context of indexing. I have all the data. I run my machine learning model on it, and then it only needs to be able to make predictions for that data that it's already seen. So in one way, this is like an enormous relief for us as machine learning people. We don't have to predict stuff we didn't see. Let's just overfit the hell out of the data, right? Awesome, okay? So, like I was saying, we just search between the bounds of the min and maximum guess. This looks like it's a linear search, but there's no reason you couldn't just do a binary search, right? Okay, that's how range queries work. The researchers also went one step further, and they talked about a lot of stuff that I'm not talking about in this talk too, but they also said, hey, we could use a standard hash table and only replace the hash function with a machine learning model. Rather than using a machine learning model to replace a B tree entirely as the full index structure, instead, we can just try to have our machine learning model predict a good integer, a good location within the secondary data store, the hash table, in order to store our data there. And then we can use linear chaining, or linear probing, or chaining, or cuckoo hashing, or whatever, and use the hash table in exactly the same way with a different mathematical model to produce the hash code. Instead of a hash function, 3 XORs, something like murmur hash, we'll use a machine learning model. Why not? See what happens. Okay? Last little piece of key insight before they started away is they realized that the last mile accuracy is really important, and that having one big complex model wasn't super helpful at getting them quite precise last mile accuracy. So instead, the researchers did all the results that we're going to see in the tables I'm going to show are a 2-stage recursive machine learning model where each of the stages, so at the top level you have one neural net, you input the value, the key you're looking for, to that neural net, it spits out a value that isn't related to the actual location in memory, but tells you instead which of about 100 other simple machine learning models, simple neural nets to use. And that second stage neural net is the one that did the actual prediction. So they subdivided the overall database structure into different sizes, and you'll see on the table they did like 10K and 50K and 100K entries, and trained on using this hierarchical model to say the first one just predicts which member of the second stage hierarchy to use. The second stage hierarchy predicts where in memory the address is, and then we search in the actual database based on that second stage learner. Okay, and all of these for this particular paper, they only used neural nets. That's the only machine learning model they did, and they were simple neural nets between 0 and 2 hidden layers, maximum of 128 nodes per layer. They found actually the simpler models tended to do better. So we're talking on the final layer, their final results were 0 hidden layers, just single layer neural networks with about 128 nodes. So you can train those things pretty quick. They're dumb. You can write one in TensorFlow in less than a minute, right? Boom. So pretty cool. Similarly, to kind of compare apples to apples as an argument, and I don't know, there's an argument to be had there, but they also used relatively naive versions of hash tables and B trees. And that's where a lot of the pushback about this paper came from. The researchers were like, hey, the state of the art in hash tables is way beyond the hash tables that you all used to compare your machine learning models to. So, take your results with a grain of salt. And fair enough, right? Okay, and then finally, like I've been saying throughout the talk, they focused on only create once, read only indexes, which is, a pretty big difference in terms of real world use cases than having a database index structure that can actually update itself when you make a new record. Now, it's not to say it's entirely unrealistic. There are plenty of situations like data warehousing where your use case is you have a backup from your main database once per day, and you re-index once per day. And these machine learning models are really good at that use case because rebuilding the index from scratch every day, whether it's a hash table or a B tree, is already pretty computationally expensive. So we can just retrain our machine learning model once per day with similar computational intense process. But here's the results. Sorry for the graininess of the image. This is just what was in the paper, so we kind of have to live with it. This data set that they ran their indexing structure on is a collection of web requests to a university's website. I'm assuming it's MIT because they're the ones who wrote the paper, but the paper didn't say it was MIT specifically. And they're indexed by date of access, which you can imagine is a relatively irregular data distribution, depending on what the holidays are, when finals are, what the course schedule is, this kind of stuff. And it was over the course of several years that they created this data set. So the big savings, what I want you to check out, is this size savings over here. So the top few rows are B trees with different page sizes. This is 16 entries per node, 32 entries per node. They chose the baseline as 128 entries per node. That's an arbitrary choice, but it doesn't really matter because all of the machine learning models were way more memory efficient. So they were able to, instead of building out a B tree that contains one entry for every single item that's in our data store, and maybe some wasted space depending on how many items there are per node and how the balance works out for those items, we're able to just store really efficiently the matrices, essentially, that represent the neural network under the hood. And turns out those matrices are a lot smaller than the overarching B tree structure. And not only that, the lookups were actually faster, which is pretty amazing. Okay, so compelling evidence that we're on the right track. If we look at the comparison of the hash table, where you replace the hash function with a machine learning model, we also see, and this is a misleading chart because you'll notice the model hash, that's the machine learning model, is always slower. They did not put the red and green in the places where they're failing. But it's very interesting that especially in this weblog data set, that's the data set that I just described with a very irregular distribution, with the weblog data set using the model hash, they were able to significantly reduce the frequency with which there were collisions in the overall data structure, which means they were able to better utilize the space. 78% better space utilization, which is pretty amazing. All right. Here's some summaries about what the authors of this paper learned. First, all of the previous classical indexing structures are agnostic to the data distribution, and maybe that's not wise. Maybe we should start building indexing structures that can take into account the distribution of the data. And machine learning is obviously a great way to have a machine think about the distribution of your data. Okay? Next, overfitting is kind of the goal in this context because we never have to understand or make an accurate prediction for anything that's been left out of the data set. We already have all the items in our training set that we're ever going to need. The training set is the test set. Hooray. Love it. Okay? They found that when optimizing their ML structures, they cared a lot more about the size of these error bounds because the size of those error bounds causes you to do a search, an actual binary search on the data itself, which can be really slow. So getting your average accuracy down is usually a more common goal for machine learning people. And in this case, it's more about reducing your worst case error. But combined with the fact that the training data is the test data, that helps us a little bit to do that. Okay? Here's another point, and this is really interesting and explains some of the size and space utilization improvements, is that in classical indexing structures, every time we insert something into the database, we have to make a new record somewhere in either the hash table or the B tree. Everything takes up space. But when we're talking about machine learning models, they already have, even at a small size, you can really efficiently store a 2 hidden layer, 128 node per layer neural network. In memory, that's still really efficient to store as a matrix or a series of matrices. And the complexity that that represents is already enough to represent a huge range of values. So it's not clear at all that with machine learning indexes, as the size of the data grows, the overall size of the machine learning models that you actually have to store, it's not clear that that gets much bigger because there's already enough complexity in the model itself to make predictions over a very wide range. Okay? Here's a really interesting argument that people in the paper made. I loved this one. Moore's law is dead or dying, and CPU speeds are not really getting any faster. These indexing structures that have been studied since the 70s have been optimized exclusively for CPU speeds. But now that those aren't getting faster, and ML workloads are a huge driver of industrial research onto GPUs and TPUs and new computing hardware, these models are going to get faster just as a result of the hardware getting faster. Whereas that used to be true in the age of Moore's law for these classical indexing structures, but isn't really true anymore. And these classical indexing structures, are not optimized for high degrees of parallelization or SIMD operations or anything like that. Okay, last lesson learned. And this is really more speculative than anything. They didn't actually do any research on this particular point, but they suspect that it might be very easy compared to classical indexing to build multi-dimensional indexes where I want to answer the question not, where's Tim in my database? Or give me all the people age 5 to 12, but find me all of the people whose name starts with a T and are age 5 to 12. Doing multi-dimensional indexing is really easy to extend this machine learning concept to because you're just like, okay, now my data's got one more feature, boom, run it through the same model, we're done, right? Whereas in classical indexing, you have to just build 2 indexes for that. You've got to build 2 B trees. So that's it. That's my talk. Thank you so much for being here. I can take some questions if there are any. Let's go right here.
My question is regarding the implementation of these algorithms. So whenever we talk about a machine learning model, there's always an input vector and then a number of features, right? So what would you consider features in this case?
Right. Okay. So the question was, in the implementation of these machine learning models, we talk about, all the different features of our data and what to predict. What's our X, what's our Y? What are the features for this particular use case? And the feature is the key that you're looking up. So the feature would just be, in the case of like a name index, it would just be the name, Tim or Ted. Make sense?
Just one feature.
Yeah. That's right. Yeah, just one feature, very simple. And that speaks to the point that the authors make at the end of the paper about these multi-dimensional indexes. They think there's certainly promise in exploring those, but because the classical indexing structures are just single feature, basically, models, that's what they were comparing to, so that's what they explored. They'd like to explore richer feature sets, more dimensional indexing structures, but they haven't yet. You had a question?
Yeah, the space savings and the speed ups are two different percentages, right?
That's right.
Yeah, those are both for traditional hashing techniques or the latest ones? Because you mentioned that.
Talking about this chart here?
Yeah, no.
This one here?
Yeah.
This is compared to B trees.
Okay.
But yes, not like the most highly optimized B tree in existence. I think the paper says which one they used, and it was basically a standard C library. Yeah, so there are some, and there was some pushback from some other authors that say, there actually are a few SIMD optimized B tree structures and some other state-of-the-art indexing strategies that get similar performance, they say, to these ones. And the researchers say, yeah, that makes sense. We also did very simplistic machine learning models, so we'd like to escalate the research, and we're glad for your pushback.
I assume this is on one core, one thread.
I'm not confident about that. I'm sure they say so in the paper, but I'm not 100% sure. I know the machine learning models, they made it sound like they were running on a CPU, not a GPU, which is interesting.
Because the memory savings are actually spectacular.
Yeah, right?
The interesting part, yeah.
Totally.
It's okay, yeah.
Yeah, and
You can parallelize that, so.
Exactly. Yeah, and the speed, they expected the speed to be slower, so the fact that it's faster at all was kind of like, oh, whoa, neat. Yeah, Brian.
Okay, I don't have a great question, so it's going to come off as a comment. I think they're missing, one of the things, think about the idea of building on better features. If you think about it, deep learning models are really great at learning features, like, for example, convolutional LLMs to learn about images. This is the path forward to build an image-based database. You could just build the index of the database on learned image features. So you could build an image database saying, show me all the small eyes, show me all the big dogs. And you could build bespoke image-based indexes for image databases, which has never existed.
Yeah, that's a great idea. Patent pending. Yeah, none of you can have it. It's mine now. Thanks, Brian. I'll give you some royalties. I think that's an awesome thought. Yeah.
Start the company. Let me know.
There a VC in here? Okay. Anything else? Folks are ready for spring break? Okay, great. Well, then thank you so much. And I'll be around here if you want to ask a question that's not in front of everyone.